Hi everyone, I will introduce our paper Patch-Based Selection and the Refinement for Audio Object Detection. My name is Tianyi Zhang, and I finished this paper with Kishore, Yaoxin, Baoxin, Jae-Sun, and Zhuo. In this video, I will introduce these sections one by one, the backgrounds, our proposed approach, and the experience and the conclusion. Audio object detection is a very important task, especially for the real-world scenario, like the autonomous driving. As you can see in this image, you can find that the objects are very small, and the ratio of these object pixels to the whole image is only 0.2%. Since that we don't have enough data volume for accurate object detection. And in the right image, we run experiments for different ratios of object pixels. As you can see, when the ratio gets more and more, the early performance, like the MAP, will decrease significantly. To solve this issue, we can try some image refinement method to upscale these images to be a higher resolution image, right? But actually, the traditional image refinement methods, they can only scale these images up with only a small factor, like 2 times or 3 times or 4 times. So actually, they cannot effectively enhance the early performance. Recently, the diffusion models show a great power for image generation, and with conditional diffusion models, we can enlarge the images with a large factor, like 8 times. But the thing is that the forward path and the reverse sampling path, both of them are very expensive, and the computation cost is very high. To address this issue, we can split the images into some small patches and process only the important patches with the conditional diffusion models. By this, we can reduce the computation cost very much. Now I will introduce the details of our approach. Our approach is the dichotomized patch refinement, DPR. Basically, it will split the images into some small patches, and there's one patch selector. It's a transformer-based network, so it will select the patches which contain objects. And for these patches, we will deal with them with CDM. It's conditional diffusion models to generate the high-resolution patches. And for these patches which don't contain objects, we will simply interpolate them to be the same size. Finally, we group them together to be the full image for the following task, like OD. In this page, I will introduce the details of our patch selector. As you can see, it's a pyramid structure. The input image will go through one embedded layer. First is a convolution layer. After that, it will go through several transformer layers. For the transformer layer, we adopt the structure of swing transformer. And we can generate the features with different scalars, as you can see. And we will select 3 of them for the classification. For the classification layer, we will introduce a learnable token to classify the patches with close attention. After that, we will combine 3 of them together to be the final output. And for the loss function, as you can see in this equation, we consider all 3 scalars. We have run some experiments to explore the image refinement for the OD improvement, like under which conditions, compared to the interpolation, the image refinement can achieve significant OD improvements. And we found actually there are 2 conditions. First, the image quality should be better. Second, we can scale the image up with a large factor. This is because for a small factor, the simple interpolation actually the image quality will also be very good. So the improvement from the refinement method will be not enough, right? And actually we find the conditional diffusion models, CDM, indeed satisfy these 2 conditions. And there are 2 paths for the CDM. First one, the forward path. So it will keep adding Gaussian noise to the original images over t steps. Finally, we get a pure Gaussian noise image. So X0 is the original image, XT is the final one. And as you can see, this is the noise mean, and this is the noise covariance. So for the second one, the reverse sampling pass, we will predict the added noise from the noisy image and condition on the low resolution image to predict the noise. And after that, we can recover it from on the noisy image step by step. Now I will introduce the experiment and the results. In this page, I will introduce the datasets and the evaluation metrics. So we use the BGD100K dataset, and here's the image size. And actually, we split the BGD100K dataset into several subsets for our purpose. And we selected two of them for our experience to verify our idea. So the first one is the FBDD. The object ratio is less than 1.5%, so the object size is very small. And for the MBDD, the object ratio ranging from 15% to 23%, so the object size is larger. And for the metrics, we have several metrics for the patch selection, the LU, the core, and the F measure. The MAP is used for to evaluate the object detection, and we have several metrics for the image quality, such as PSNR, SSM, and FID. This page shows the results of the CDM for patch refinement. In this table, shows the comparison of the CDM, computation, the diffusion models, and the BI, the bilinear interpolation. As you can see, for the 4 times upscaling, you can find actually even for our CDM, the MAP, the OD improvement is not very significant. But for 80 times, you can find that the OD get improved a lot. So it matches what I just introduced previously, right? We need to upscale with a large factor to improve the OD. This page shows the results of different patch selector structures. As you can see, after we introduce the random token to classify with close attention, you can find we achieve better in performance. And also for the pyramid structure, the performance gets improved a lot. And also for the weighted cross-entropy, you can find only the GPR gets improved. So it means that the information loss will be less. For the red table, the value denotes the number of transformer layers. So actually you can find with 4 layers, actually the GPR is pretty similar to 6 layers, but the computation cost will be much less. So actually we selected this one as our optimized structure. This page shows the OD results with selected patches. As you can see, both diffusion models can achieve better performance than the bilinear interpolation, and you can see our DPR could achieve slightly better performance than SR-Sun with only 22.8% of the computation cost. This page shows the OD results with the finder full images. As you can see in this table, we can find that our DPR effectively improves the OD performance a lot. And actually you can find that the swing IR performance very bad. This is because it is a transformer-based structure, and it can upscale the images only with a small factor. This page shows the visual comparison of generated images. As you can see, the images overall look pretty similar, but for the objects, you can find our DPR show much better details. So by selectively refining the patches with CDM, our method efficiently enhances the OD performance, like MAP from 1.03 to 8.93 with much less computation. Thank you.